In this geometric optimization problem, we're going to minimize the cost for making the following cylindrical can. The question says this: a manufacturing company is responsible for designing a 2-liter cylindrical can for apple juice. The bottom of the can is made of metal that costs 4 cents per centimeter squared. The sides of the can cost 3 cents per centimeter squared, and the top costs 2 cents per centimeter squared. What dimensions will minimize the cost of producing the can? Now, this may not quite be realistic, but the idea is that we're going to have most of the weight on the bottom likely, provided we actually put this the correct way on the shelf. And so that's why it's going to have to be the thickest, and then the least weight on the top, that's why it's going to have to be the thinnest. So one could assume here that cost is related to how thick the can is at different points. First thing we want to do is draw a diagram and label it. Now you see I have my cylinder there. I've labeled my radius, I've labeled my height, and we can go ahead now and create a formula for the property that's to be optimized. So the second step is doing that. And so the surface area is equal to, now in this case, let's look at it in terms of the top and bottom separately because they're different costs. We'll get to the costs later, but right now we're just starting with the surface area. So we have pi r squared, that's the top. And the top is labeled as such because that's a circle. The area of a circle is pi r squared. The bottom is the same, and so pi r squared for the bottom. Now we move to the sides, and the sides is a circumference times height. And the circumference is 2 pi r, and the height is h. Now if we're trying to put that in terms of cost, I can put that in terms of cost in dollars, or I can put that in terms of cost in cents. I'm going to do cents. They're both going to work out the same way for the correct answer, whether you do dollars or cents. But cents is just an easier way to do it because we're dealing with whole numbers instead of decimals. The bottom of the can, let's start there, is 4 times pi r squared, 4 cents. The top of the can was 2 cents, 2 times pi r squared. And the sides of the can was 3 cents, so 3 times 2 pi r h. And so now what I want to do is I want to simplify this equation. And what I can do here is I can bring these two terms together, and that's going to give me 6 pi r squared. They're like terms, so I can add the 2 and the 4. And then the 3 times 2 on the other term gives me 6 pi r h. And so that's my cost equation. But you'll notice that I can't really solve that cost equation because I have two variables that it's equal to. There's the r variable, the radius, and there's also the height. And what we want to do now is find an equation for the variable that we only have once in the equation and substitute that in so that it simplifies things for us and puts cost only in terms of one variable. And this variable here is going to be the radius. What we're trying to do now is find a formula for the constraint property. Because in reality, we have not dealt with this 2 liters yet. We've dealt with the cost, but not the 2 liters. And so the volume is equal to pi r squared times h. Pi r squared times h. What we can do with that is we can say, well, 2 liters is equal to 2,000 centimeters cubed. 1 liter is 1,000 centimeters cubed, and so that's going to give me 2,000. So I can replace the volume with 2,000. We get pi times r squared times h, and now I can isolate h by dividing by pi times r squared. Whatever you do to one side, do to the other. The pi r squared cancels out, and we get h is equal to 2,000 divided by pi r squared. And now what we're going to do is we're going to sub that in for h. And so now we're going to get our cost equation in terms of only one variable. So we're now combining the equations to eliminate unknowns. 6 pi r squared plus 6 pi r. And when we substitute in the h, we get 2,000 divided by pi r squared. So the pi is going to cancel it with the pi. This r is going to cancel it with one of the r's. And we're going to be left with 6 pi r squared plus 6 times 2,000 is 12,000. And then we have an r on the bottom, which we can write as r to the negative 1. Because if you bring it up, it makes the exponent negative. And so the reason I want to do that is just going to make it a little bit easier to calculate the derivative here in a moment. But this is our cost equation now in terms of only one variable. It's only in terms of radius. And so now we can use that to minimize the cost. So let's go ahead and find the derivative because that's going to allow us to find the maximum or minimum after we set that equal to 0 and solve it. So the derivative of the cost equation, we'll call it cost primed, is equal to 2 on the r squared is being multiplied by 6, so that's going to give me 12 pi r, and we write that to 1 degree less, which is just 1. I don't need to write the 1 there. and then that's going to be plus. Now the r to the negative 1, it means I'm going to multiply negative 1 times 12,000, then multiply that by r to the power of 1 less, which is negative 2. I can simplify that further by writing this out as cost primed equals 12 pi r minus 12,000 times r to the negative 2. Now what I want to do with that equation is I want to common factor out whatever I can common factor. I can take a 12 out of both those terms, and I can also take the lowest power of r out. And so the lowest power of r is r to the negative 2. What that's going to leave me with in the first term is it's going to leave me with pi times r cubed. Because r cubed times r to the negative 2 gets me back r to the power of 1. And then we're going to subtract 1,000. And we've taken out that r to the negative 2, so there's no r term on that second term now. So we're going to set that derivative equal to 0. So that derivative is equal to 0, and we want to solve for r. That means 0 is equal to 12 r to the negative 2 times pi r cubed minus 1,000. Let's go ahead and solve the two situations now. 0 is equal to 12 times r to the negative 2, or 0 is equal to pi r cubed minus 1,000. Those are our two possible solutions here. Now let me write this out as 12 over r squared, and I think you'll see why this doesn't give us a solution. If I try to solve this, I have to multiply both sides by r squared. In other words, cross multiply. So 0 times r squared is 0, and that gives me 0 equals 12, which is not possible. And so that's not a possible solution here. So the only solution comes from the other one. And so if I rearrange this, I get 1,000, adding 1,000 to both sides, is pi r cubed. I'm going to divide by pi. I want to isolate r here, so I divide by pi, and then I take the third root of that. So the third root of 1,000 over pi, and that gives me my radius value. And what I end up getting here is about 6.83. 6.83. Yes, now remember the units that's in. That's in centimeters squared is what we used for the surface area. So that's going to give me units of centimeters. We're going to check that here in a second, but that's the optimal radius for this. Now it said what dimensions will minimize the cost. Now remember, we don't just have a radius, we also have a height. And so we go back to this equation over here, and we say, well, that means the height is going to be 2,000 divided by pi times 6.83 all squared. And for our height, we get a value of approximately 13.66 centimeters, which is interesting because you'll notice that this is actually exactly double. It's exactly double. Now, it won't always be the case based on what you're given, but in this particular case, my height is double the radius. In other words, my height is equal to my diameter. The last thing we want to do now here is check this solution, and we do that by the second derivative test. So I'm going to take the simplified version of the first derivative that I had, and I'm going to take the second derivative of this. So that second derivative, when we take the term 12 pi r, then I just have 1 times 12 pi and then r to the 0. So that just gives me 12 times pi. And then I'm subtracting negative 2 times 12,000 times r to the negative 3. So we can write this out as 12 times pi plus 24,000 times r to the negative 3. You'll notice with this that this is always going to be positive. I can't solve any r value in that's going to make this negative. And so because this is always positive, the second derivative test tells me that that's going to be concave up, and therefore it's a minimum. So it's going to be a minimum cost when r is equal to 6.83 centimeters and the height is equal to 13.66 centimeters. And we have optimized that cylindrical can to keep the cost as low as possible for our company. If this was helpful, please check out the derivative question on the right and the calculus playlist of videos on the left. Thanks so much for watching, and I hope this was helpful.